So what about neurologic factors? Remember, morphological, yes, we've dealt with, but in other words, for the muscle to be recruited, there's a neurological factor here. So what goes on neurologically? Well, one of the things we have to understand is the neurons also adapt. And one of the things we understand is the notion of what's called myelination. And myelination is only completed in adolescence. And so until then, what we understand is that coordination and reactions will be limited and will not be equivalent to those in adulthood, which relates back to what we were saying right at the start in this presentation about coordination being impacted. Myelination is the notion of what's called the myelin sheath. The myelin sheath sits at the outermost area of the nerve tissue. And fundamentally, what neurologists have started to understand is that the myelin sheath basically is there. It creates an encasement and promotes neurological efficiency. So if you haven't got full myelination, the nerves, although they are functioning and recruiting muscle, they're doing it in a less coordinated manner. And that manifests itself in terms of the notion of being perhaps ill-coordinated or clumsy. At the same time, you've got to remember that we also recruit, or have the potential to recruit, the synergists and the antagonists and the agonist muscles. But this changes with age. And what we know, it's not until all the stabilizing muscle groups are developed and become correctly coordinated with the prime movers that the optimal exercise can be achieved. So, excuse me, when we're much younger and we've got poor coordination, we recruit more synergists, the stabilizing muscles. The stabilizing muscles come at an increased cost because you're recruiting more muscles and more muscle fibers to do the same amount of work. So you have an increased energy cost. Because you have an increased energy cost, exercise becomes harder. Physical activity becomes harder. Training becomes harder. And it's only as we start to get both the myelination, and it's only as we start to get that kind of coordination that comes with it, that we down-regulate the use of the synergists and we up-regulate the recruitment of the agonist-based muscles. And then we start to become more coordinated, the energy cost starts to decrease. But it does make you wonder why, in a vast majority of sports, why it is, and this is something to go away and think about, why do we promote technique and developing technique in adolescence? Because that's where we do it. If you think about sports like football and rugby and cricket, netball, and even if you think about sports like, track and field, where we're, promoting sprinting technique, for example, we're promoting all of those kind of skills and those techniques in adolescence. We don't think to promote those in young children, primarily because we tend to assume that they won't understand what is going on. But look, fundamentally, you're not going to achieve much because coordination is impacted. So the motor programming that you're trying to develop is being impacted because of a lack of myelination and an increased recruitment of less efficient synergistic muscles. On top of that, there is the ability to use stored energy. As we get older, we go into adulthood, our capacity to use stored energy, remember you have potential energy and then kinetic energy. Potential energy is that which is stored in the muscle. So we know that eccentric muscle actions are far more efficient than concentric muscle actions. It's the notion of a muscle acting and working like a spring. And this is the notion of muscle stiffness. We know now, we're starting to understand now that muscle stiffness reaches, again, its kind of peak capability in our early 20s and then starts to dissipate with age. And so this ability to store potential energy starts to develop. We're not very good at storing it. Why? Particularly in youngsters, because of the recruitment for less efficient muscle fibers. As we start to recruit the appropriate muscle groups and we start to get appropriate neural recruitment, we start to be able to use the muscles appropriately. We start to be able to engage with the storing of energy. We start to be able to use eccentric muscle contractions more efficiently. And therefore that has a ramification in the total amount of energy that's also being used. Remembering eccentric muscle actions are far more efficient than concentric muscle actions. So if we look at this data, they're not particularly easy graphs to perhaps understand, but what we've got here is we've got changes in myelination rates in infants recorded, and these are the superficial and deep occipital nerves. Okay, so if we kind of just follow the data, it doesn't really matter which group you're looking at, but what you can see is here's the age, okay, and here's the degrading of myelination, and they've plotted the data in kind of two different ways. But can you see that fundamentally, here's our kind of rate of change here. Look at this. You're getting the sudden acceleration in myelination, then it starts to slow down. And even if you plot it in this way, you can see that myelination it's perhaps more delayed. This is the one you perhaps want to follow in terms of the data set. And you can see over here as well in this data set here. They're both showing pretty much the same data, whether you're using the superficial or the deep occipital nerves. And you're seeing this kind of myelination increasing over that period of adolescence in both of those charts.